Good morning. Welcome back to Sustainable Manufacturing course, wherein we are trying to learn how to get a sustainable system using certain techniques, that is green techniques, starting from very unit manufacturing process to final manufacturing concern. So in this lecture I'll discuss green machining techniques, and the contents are: first we will see what is a machining process and what are inputs and outputs of a machining process, and we will see what are cutting fluids and what are various characteristics of these cutting fluids, the benefits and limitations or hazards. Then we will discuss a few machining techniques which are termed as green techniques. Now I will start with the machining process. What is a machining process? If you could remember, we had that temporal aspects of a system in which we have the very process control to the whole system level control here, and we see that here we had the time from milliseconds to days, and we saw that here we had the process control, and we have certain other things, and here we had the supply chain management. Now here we will talk about this thing, process control only. So in machining process is a process which has materials, energy and human or personnel or the operator that works on it, that has to do the machining as its inputs. Herein the material may be my workpiece, then fluids, that is coolant and lubricants, coolants or lubricants, and tools. So what is this? In this case the tools are expensive and the cost of cutting fluid also varies from 14% to 20% of the machining cost. So regarding tools, we need to minimize tool wear, and regarding workpiece, we need to minimize scrap, that is the chips that are produced. So this is our purpose. So this was my material. Next is energy. Now energy is consumed in machining itself, and other components, other systems in my machine tool, that is our fluid supply system, then lighting system, and similar systems also consume energy. So here what we are more concerned about is the variable energy. The energy is like this in machining, that there is some fixed amount of energy that is our cooling. In case of flood machining, the coolant system has to keep on running, so there is some fixed energy. So there, this machining is my variable energy. So our purpose is to reduce this machining energy, this variable energy, to minimum. And even this energy, if some system we can omit, this energy can be brought to the lower side. So the total energy would be like this. So in case of human and it also I would say human and documentation here. So what do we have here is technical documentation, then human has to handle our workpiece, he has to handle the cutting fluid, then maybe chips manipulation. And certain jobs like this, if our machining is very conventional machining. In case of automated machining, for example in CNC machining, certain things are automated. So in case of CNC machining or certain automated machining, the worker involvement is less. So in that case, the cutting fluids etc. all are controlled by an automated system. Even the machining is done by that. The worker does not have to control the flow or the feed of the tool. So the most of the machines which we have used in our lab demonstration are automated machine only. So this machining process has these inputs. These major inputs are materials, energy and human resource. So these are further classified, I have further detailed a bit. Now we have outputs. These outputs are heat. I start from the environmental outputs here only. Now heat goes to atmosphere, workpiece, chips, coolant. This is actually, we have heat affected zone where this heat is dissipated to atmosphere, then it goes to the workpiece as well. That may deteriorate the quality of my workpiece, maybe surface finish, and chips also carries away some heat, and most of the heat is carried away by cutting fluids, which is one of the fundamental purpose of using cutting fluids. So next, with heat we have certain other emissions. This actually comes under emissions. If I say emissions, so one is heat, second is air emissions. Air emissions are the aerosols if produced, the chip particles that are too small that goes into air, and we have other emissions, that is water emissions. Water emissions, that is my cutting fluid goes over here. It goes for here either for recycling or for disposal. Then chips are a kind of solid emissions. Solid emissions are chips. Then okay, I directly came down to the environmental outputs here. The major outputs here would be my machined or processed material, or I could even say product of this process only. Then we have scrap. So these are our major outputs. So next, before discussing the green techniques, I like to put some light on cutting fluids. So what are cutting fluids? Cutting fluids are used in metal machining for a variety of reasons, such as cutting fluids improves life of tool, then reduce workpiece thermal deformation, reduce workpiece thermal deformation. That is, it controls the heat emission. And on the top of it, it also improves surface finish and flush away the chips. And flush away the chips. So the major kinds of cutting fluids are straight oils, soluble oils, semi-synthetic and synthetic fluids. And synthetic fluids. So these are very general kind of cutting fluids, those who are available in the market since the machining process started. So these days also we have biodegradable fluids. Now straight oils are non-emulsifiable and used in machining operations in an undiluted form. So these are undiluted. They are composed of a base mineral or petroleum oil and often contains polar lubricants such as fats, vegetable oils and esters. And the major additives here are chlorine, phosphorus and sulfur. So these are the elements, those are not very environment friendly, this phosphorus and sulfur here. So next kind of cutting fluid are soluble oils. So soluble oils are, if the name itself suggests that they are soluble, that they are used in a little diluted form. So the soluble oils is an emulsion of water and straight oil. This is water plus straight oils maybe. Now these emulsions are made from alkaline inorganic or organic compounds along with certain additives that are used to reduce corrosion. So these are generally diluted in 3 to 10% in the water. So, they are widely used in industry and are least expensive among all cutting fluids. So, these are the major cutting fluids, those are used in industries. Major use, right. Next we have synthetic cutting fluids. Synthetic fluids does not contain any petroleum or mineral oil, but they are formulated from inorganic or organic compounds. Formulated from inorganic or organic compounds, and their cutting performance is best among all the mentioned. However, they are not very environment friendly. Here by best I say, if I compare the four these kinds of fluids, its performance, if we do not use any modern kind of additives, this performance may be said as best. But these days we have nano fluids or nano additives that can be added, that even can produce better performance using biodegradable fluids as well. Better using some additives. One of the additive here, one example here be molybdenum disulfide. So, semi-synthetic oils are essentially the mix of the synthetic and soluble oils. So, these are synthetic oils plus soluble oils. I would add here the soluble oils here may be water plus the straight oils, or maybe water plus emulsions also. Certain emulsions also be used here. Emulsions or straight oils, right. So, next we came to the biodegradable fluids here. So, these are actually vegetable or some organic fluids, those are biodegradable, those do not affect our environment. So, I will put some more light on this later. So, this is a general flood machining. In flood machining, the fluid jets are flooded on the machining area. So, this is drilling is happening here. So, this drill is going in and this one is rotating. It is trying to make a hole over here in the workpiece. This is my workpiece here. So, these jets are put on the workpiece here at the tool work area to flush away the chips, to dissipate heat and to perform its other functions. So, in this case the fluid flow rate is from 4 to maybe 10 liters per minute. So, you can see that two jets are heavily flooding this workpiece. So, this is taken from a reference. So, now these cutting fluids are to be selected using some criteria. So, the fluid selection criteria may be its performance, its heat transfer performance, would say cutting fluid selection criteria. Then we have lubrication performance. Then chip flushing. So what I am trying to say here is that in case of chip flushing, when we do some fine machining, the size of chips that is produced is very small. So in that case, a very small jet or very slow speed jet can also work. But when the chip size is very large, or even that is when the depth of cut is high and that coarse chips are produced, or when the metal that is being used has some properties that the chips is trying to stuck to the workpiece. So in that case, this cutting fluid also helps in flushing away the chips. This is one thing. Dissipating of heat is the other thing. Lubrication is another thing. So there are certain other criteria here. For example, if we use MQL, then fluid mist generation. Not even in MQL, the fluid, when it is flushed away, on the workpiece, some mist is produced. That is how much mist is produced in the atmosphere. That is also one of the criteria. The mist generation property of the fluid, that how much mist is generated, what is the viscosity, is one of the factor that would play a key role here. Now another criteria here may be fluid carry off in chips. Fluid carry off. Fluid carry off by chips, maybe by workpiece. If lubrication is there, some fluid is even carried off by this one only. Then another criteria here is how much corrosion is inhibited by this one. And in some cases, the stability of the fluid, that is my emulsion stable or not. In case of emulsions, this is my mixture that I had made it with my water, does that remain homogeneous or does it separate after some time, and after how much days does it get separated. In general, the cutting fluids, those are filled into the reservoir, are disposed of in a week time in general. But in some cases of machining, maybe in a day, maybe multiple times in a day, the fluid reservoir may be refilled with a new fluid, with a fresh fluid here. So this stability of emulsions is important here as well. Next, these kind of performance were just the process performance. So this criteria is the process performance criteria. I would put it number 1. Now number 2 is my health hazard. Health hazard performance, I would say. So there are certain occupational health hazards associated with cutting fluids. Occupational health hazards, for example, skin diseases, eye rashes, maybe some cardiovascular disease. So these mechanisms are essentially based on the external or internal contact involved in machining work. That is, does our worker touch the fluid physically, or is he breathing or inhaling this cutting fluid? Then is how much is fluid being splattered, splattering of cutting fluid, and maybe splattering or splashing here as well. Then is mist able to be settle very soon? Mist, first we would say how much mist, amount. So is it settled soon? Now in what time? So these are the factors that affect the occupational health here, the health of the operator who is using this machine. Now the mechanisms include the chemical toxicity of the fluids as well. So here chemical toxicity of fluid also plays an important role. I put it here only. Chemical toxicity and physical irritating ability. Of my cutting fluid, of the cutting fluid being used. So what causes this toxins, what causes this chemical toxicity in my fluids, what made it physically irritating? So it is essentially the metal particles itself, it is the major contributor here. So along with this other additives and inhibitors, those are added, also have certain bacterial or fungal populations, bacteria or fungi. So these atoms in the fluid, then maybe biocides, right, then the corrosion inhibitors, those are added. So these are the things that make it chemical or physically irritating to the human being. Along with this, the next criteria, this criteria for selection of cutting fluid is environmental criteria. Environmental criteria mainly involves the disposal or recycling of our cutting fluid. Now disposal means, so cutting fluid has to be disposed in water. How much water intensity, or I would say intensity or impact. So what is environmental impact of the water that is getting dirty because of our cutting fluid, and what are our recycling cost? Then is it available locally, the recycling plant? If not, what is if not? I can have a secondary factor here, what is transportation cost then? So regarding the disposal of fluids, it is also important to maintain the cutting fluid characteristics before disposal. Maintain before disposal. The maintenance involves the checking the concentration of soluble oil emulsions, maybe pH value, the quantity of tramp oil that is leaking into the cutting fluid system, and maybe the quantity of particulates those are in the fluid. I can put it here, the pH value, then particulates, then tramp oil. This is important here. Now action those are needed to maintain the fluid includes adding makeup of a concentrate of water, then skimming of tramp oil, adding biocides, and some process to prevent bacterial growth, then filtering the particulates maybe by centrifugal forces. Now the cutting fluid within a coolant system degrades with time and has to be disposed sooner or later. So this disposal does happens sooner or later, this would happen. Now then comes this water intensity, the water impact. When it is disposed, what is the impact on our environment? So with time, the bacterial growth and contamination with tramp oil and fine metal swap from machining operation, the fluid becomes very bad and it cannot be used. So then it becomes essential to dispose of this fluid. So this is then dumped. Now prior to letting the fluid to flow into the sewer system, it should be treated. So the treatment is also done here, so as the water intensity or water impact here is lower. Treatment to lower the environmental impact. So generally the toxicity or the chemical or the physical irritant capability is not very high, but it's sometimes enough to cause problems like these respiratory problems which I mentioned here, and eye rashes, skin diseases, then certain alimentary tract could also come in, then allergy, occupational acne, then asthma, these kinds of things, then hypersensitivity, these kinds of health hazards could come into picture. So owing to all this, the cutting fuels were called as necessary evils. In machining. Now this statement was being said a few decades back. Why necessary? Because they have these functions without which a good machining cannot be performed. Why evils? Because it has these hazards and environmental impact as well. So then there are certain approaches, those eliminate the use of cutting fluid. For this, the most radical approach is do not use the cutting fluid at all. Hey, dry means dry machines, that is no use of cutting fluids. Another process similar to this may be near dry. In near dry process, that is also called as minimum quantity lubrication process, in which very small quantities of lubricants are used. So this is near dry process. Now this small quantity may be from 10 to 100 milliliter per hour. So dry cutting is made possible by recent developments, but there are challenges. What about these things? What about the heat transfer? What about the lubrication? So when the heat is very high, the workpiece heat would go to tool, the tool life would become less, even the heat flows to workpiece as well, no chip flushing happens, and certain similar problems are associated. That is, heat, where would our heat go? Then chips flushing, how would this happen? Then tool life, what about my tool life? If tool is heated too much during machining, how do we work on that? So this limits the scope of dry machining. All this limits the scope of dry machining. That is, we need to have a tool that is very hard and it has at red hot temperatures, it has good performance. Performance has to be high or good. So one kind of cutting tool, that is cutting material, that is used here is diamond. So diamond can perform at high temperatures, but limitations is always there. The depth of cut, we cannot have as good performance as we had in flood thing. So this can work at high temperatures. The chip flushing can be done with help of air blast. Then tool life is compensated by fluid cost, not only the cutting fluid cost, but the cost of fluid handling system. This is actually a one time cost, but some of the cost is already compensated at, some cost is. However, the dry machining cannot be applied to the tools which have titanium or chromium or nickel based alloys. So here we cannot do dry machining. So I have a dry machining video here we'd like to show. So this machining process was performed in manufacturing science lab in IIT Kanpur. So you will see a dry machining, that is dry milling of a workpiece. We are just cutting the straight slots. A CNC machines MCO concept 250 was used here. I would even show you the CNC program which I made, because in the demonstration process we like you to know the maximum details, that how green machining is being carried out, how do we select the material, how do we do machining, and everything, simulation, all the things would be covered over there. So in this case I will just run my machining process. So this is my machining being carried out here. So end mill is here held in a chuck, not chuck here, it is held in a collet here, and we have in this green color, you can see the dynamometer. This is a drill dynamometer, that is 5-axis dynamometer. So you can see that it did machining and rapidly it came back to its original position. Now it will again do machining. Some depth of cut is given, it is cutting a slot. So this is dry machining, no fluid or no mist is being sprayed over it. So it will move up and rapidly go to the third position here. So if you noticed, there was noise that was produced here. So the noise here is of the machining only. In dry machining, the noise of machining is higher. In case of coolant, there is some noise of pump, and in case of MQL, there is some noise of the air if we use the air system, pressure system to supply the fluid. But in case of dry, if I divide my noise into two categories, that is the average noise that is produced during machining, second is the peak noise. If there are some peak pulses, those are produced, those are high in dry machining. For instance, at higher depth of cuts, the noise like this kind of noise comes, that is very high. The intensity of noise or the noise pressure is of the order of 130 decibels. So that is very irritating to the human being, to the operator over there. So dry machining also have these bad effects associated with itself. So this all was about dry machining. I would like to take a break here and would continue in the next part of this lecture, wherein I will discuss near dry, that is minimum quantity lubrication, and cryogenic machining. Thank you.